Okay, so we are on to lecture 9 of 10 in this course, Material and Geometric Nonlinearity. Let's just have a little recap on what we've done most recently. So the last couple of lectures, we've started to look at geometric nonlinearity, which means that we're dealing with problems where the deformations, whilst we do the calculations, are significant and actually change the calculations we have to do. So you can no longer rely on the very simple measures of things like strains. So you have a more fundamental way of thinking about deformations, and inside this thing called the deformation gradient F, there is all the information about what is happening at the material point that you're interested in. And it is really just a mapping between where you were and where you are. So big X is where you were, little x is where you are. And remember that x, y, z can appear just as a vector x, and capital X, capital Y, capital Z can also appear. I did some slides on that last time. So we can decompose the deformation gradient into some more useful things, something that tells us about rotation, and then something that tells us about stretching. And stretching is usually of more interest because that is where we might get some failure. So failure is going to occur where we have shearing often, and that usually means a change of shape. Rotation is usually a rigid body motion, and the example I went through last time, which was, pointing the wrong way, this one up here. So imagine taking a cube and rotating it, working out what the map was between where it was and where it is, working out the deformation gradient, and then also working out the strain as measured in the standard engineering way. And we discovered that a rigid body motion would actually lead to a prediction of a strain, which is wrong. And that is because the deformations, the rotations, are now substantially similar to the dimensions of the object that you're moving. So then we moved on to try and solve that problem by coming up with some strain measures that do work. So this is page 47 of the course notes, and there's a family of these, and it looks a bit bewildering, and somebody asked me at the end, well, why do we have all these? You know, the trouble is there is no truth. It's just an artifice, really, because we are doing the measuring. We'll come on to later on why we have these different measures and what we need to do in terms of their counterparts in stress. But they do give you different answers. Okay, so we'll see why we need to have them a bit later on. Well, we need to have them because the basic measure doesn't work. So we have a family of them that look like this. So m is an integer, can be negative as well. U, that is your stretch matrix, and I is your identity matrix. And then apart from m equals 0, where we have this format here, so it's the natural log of u, which is the same as half the natural log of c, because c is u squared. And you remember how logs work. So the e to the 2 is green Lagrange strain, the e to the 0 is logarithmic strain or Henke strain, and we'll be making use of the second one of those more than the first.